Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my pleasure to introduce Ray Wang. Ray is a fourth-year PhD student at Indiana University, Bloomington. His research is focused on system security, including e-commerce security, side channel issues, privacy-preserving techniques, and reverse engineering of binary executables. He has been the lead author of many papers in top-tier security conferences, including Oakland, CCS, and Usenik Security. And this summer, he's doing his third internship with us here at MSR. And the work he's going to present today started as his second internship last year. It is about how can you shop for free online. So, Ray.
Thank you for coming to my talk. This is a joint project between Indiana University and Microsoft Research. The other authors are Shuochen, Xiaofeng Wang, and Xie Clear. In our research, we did several interesting purchases from web stores, such as this DVD shown here, and this agility cream. I guess this is for bodybuilding. Not quite sure. They're interesting because we did not pay for them, or we only paid with an arbitrary price. We found a set of logic bugs from the checkout mechanisms of the web stores. Besides buying this kind of free stuff, we do have our serious academic motivation, which is to study the API as a web service paradigm. We know that today a lot of big websites expose their web services through a set of web APIs, such as Facebook, PayPal, Amazon EC2, etc. So a lot of websites call those APIs to integrate the third-party services. Now the whole system consists of the web client, the integrator website, the service API website. I can give an example here. The web client may be the browser, and the integrator website is like buy.com, and the service API website is PayPal. So buy.com integrates PayPal and something like that. It's third-party service integration. Our intuition is that the security for such multi-party web apps can be very challenging. Of course, as system researcher, our goal is to show significant empirical evidence to support the intuition. In a multi-party scenario, from the security angle, we have to consider what if one party is naughty, just like the kid. Suppose the three parties can only communicate through one phone calls. The kid can tell mom a story X and tell dad a slightly different story X prime. So even if mom and dad communicate, if they're not smart and careful enough, the kid would have a good chance to get something that he does not deserve. So this is the intuition. Concretely, we studied today's web stores which integrate the third-party cashier services, such as PayPal, Amazon Payments, and Google Checkout. We call them Cashier-as-a-Service or simply Cash. This scenario is very important because today a lot of web stores are using cash services. Just name a few here. Now the web store only handles the order information, and the cash handles the payment. So the whole system has to make a joint decision, which is whether the shopper has made the proper payment to the order. Here I want to give you some basic knowledge about the checkout workflow. At this side, you see the familiar checkout page of the web store, and at that side you see the three parties, which is the shopper, the web store such as buy.com, the case such as PayPal. You also see the web APIs exposed by the two websites. So when the shopper is ready to check out, he clicks the checkout with PayPal button. This will generate a HTTP round trip. This consists of HTTP request rt1.a to buy.com and HTTP response, which is rt1.b from buy.com. rt1.b will redirect the browser to PayPal, where the shopper will see the payment confirmation page. So the shopper confirms the payment by clicking this Pay Now button. This will generate rt3.a, and PayPal then collects the payment, may communicate with buy.com, then respond with rt3.b. rt3.b redirects the browser back to buy.com, where the shopper sees this order completion page. Sorry.
So you like the interactive format of this talk, right? Rather than waiting.
If you have any questions,
please
feel free to ask.
Yeah.
So in this process, you see that the shopper's browser is redirected back and forth between the two websites. This is just one example. There are many other payment methods, such as PayPal Standard, Amazon Simple Pay, Google Checkout, etc. And even for one payment method, different web store may integrate it in different way. So basically, we have a lot of this kind of scenarios to examine. The problem is, why do you think that the shopper has to run a browser to do all of these communications? Actually, the shopper has the complete freedom. He can play with any of these messages because all of the APIs are exposed to the web. So under this adversary assumption, can the shopper shop for free or set arbitrary prices? Then we studied the source code of the popular merchant software, such as NopeCommerce and Interspace. Merchant software are the software used to build the web stores. Like NopeCommerce and Interspace, they are powering tens of thousands of web stores on today's internet. We also studied the Amazon SDKs, which are used by the web stores to integrate Amazon payment services. In addition, we studied the popular big store, JR.com and Buy.com, but we don't have their source code. We studied them in a black box fashion. What we found is 9 different checkout scenarios vulnerable to a set of logic bugs. And as a result, we can either shop for free or set self-determined prices. Due to the time limit, we only talk about 3 of the bugs in this talk. Also know that we only talk about the high-level summaries of the bugs, and some subtleties in the source code are critical but cannot be covered here. Please read our paper to understand the complete story. We only talk about from the high level, what's this kind of things look like.
Was it easier to attack the open source sites or the two closed source sites?
Yeah, we first studied the open source merchant software, and also some commercial merchant software. They sell source code. We still can buy the source code. Yeah, and also we studied those big stores which we do not know what source code they are using. Then we studied through.
Was it appreciably harder than JR.com? For you?
Not. I think without source code access, you cannot thoroughly check what kind of problem they have. But by using the experience we gained from the source code analysis, And also by reading the documents, like PayPal provided, we still can understand more about the traffic, not just look at the plain traffic. You actually have a lot of context. Yeah. The first case is about the merchant software no commerce integration of Amazon Simple Pay. This is the figure of this kind of communications back and forth, and also the merchant side logic. And this figure is a little bit complex. This is shown in the paper, and but let me try to give you a simplified story, because it's kind of a little bit complex and cannot be talk about this figure here. A simplified story can be start from the benign shopper Chuck, who want to buy a DVD from the web store Jeff. Jeff will compose a signed letter and ask Chuck to forward to Amazon to do this payment. The letter says, "Dear Amazon, order 123 is $10. When it is paid, call me at 425-111-2222. So Chuck will just forward this letter, and Amazon then verifies this signature and ask Chuck to do this payment. Then call the phone number, and Jeff will then ship the product. The phone number here is analogs to the return URL. Actually, all of these communications are HTTP on HTTPS. They are just HTTP messages. And this scenario is more or less common sense, similar to a real-life purchase. But in the online world, anyone can register an Amazon seller account, so can Chuck. So what we did is to purchase a $25 MasterCard gift card. There is some kind of, this type of gift card, which is called a MasterCard. And also, you can also purchase Visa gift card. And this kind of gift card, we purchased by cash. We didn't show our real identity. Then we found that we can register we first register the card under the fake name Mark Smith with the fake address and phone number. Then we found that this kind of MasterCard gift card can be used to register for seller accounts in all the cash services. So Shopper Chuck also plays seller mark. He tells Jeff that I want to buy this DVD, and Jeff will give him the same letter. Now, instead of forwarding this letter to Amazon, Chuck replaces the signature with Mark's signature, because Chuck now has the signing ability of Mark. And for Amazon, he only sees the order of Mark, has nothing to do with Jeff. After the payment is done, Amazon calls the number, but the number, actually the recipient is Jeff. So for Jeff, he indeed has a pending order, which is 123, and he verifies the signature, which is indeed Amazon's signature. So
I gather Amazon does not link the signature with the phone number or HTTP address. The signature, it's any signature, and it goes, and you can mix it with any phone number. Well, not any, but
yeah, the phone number is in the message and is protected by the signature, but Amazon does not guarantee that this phone number is exactly Mark's phone number.
A little bit of clarification. So here the message is signed by Amazon, and it is always signed by Amazon.
Yeah.
So there is no linking here. What you were saying is the linking between the return URL and the previous, the signature on the previous message, which is now Mark's signature. Right?
that's missing.
Yeah, that's missing. Yeah.
Thanks.
So Jeff does not anticipate that Amazon will send him a notification, which is completely irrelevant, because Amazon essentially says to Jeff that Chuck just paid Mark $10 for his order 123, and Jeff will finally ship the product. So in this case, Amazon thought that Chuck was buying from Mark, but Jeff thought that Chuck was paying to Jeff, and this gap caused the problem. The second case is about the merchant software Interspace integration of PayPal Express. Again, this is the figure of the communications shown in the paper. Let me try to give you a simplified story. Suppose we can only have one shopping session, which is for this chip order, order ID 1. This is the sketch of the communications shown in the previous slide. The most important message is RT3.B, which is an intra-website redirection. And the intra-website redirection will call the API update order, in which the store attach argument, the ID, order ID 1, and signed by the store. T star denotes this signing, so the shopper cannot tamper with it. And honest shopper will just do this redirection. But let's see if we start a second shopping session. This time we place an expensive order, order ID 2. We then skip the payment step. The interesting thing is we still can get RT3.B, in which there is order ID 2 signed by the store. So the next thing is pretty simple. Just copy and paste this value to RT4.A of the first session and release this message. And in this way, we can check out the expensive order from the first session. The third case is about Interspace integration of Google Checkout. High-level summary of this bug is the payment total is calculated at the moment of RT2.A. That is when the shopper clicks the checkout button, and the order is created at the moment of RT3.A. That is when the shopper clicks Pay Now button. So there are 2 moments, and between the 2 moments, the shopper is allowed to add more items. So then things become simple. You just place a cheap item in the shopping cart, then you click the checkout button, then add more items and click the Pay Now button. This way you only pay for the cheap item and you check out the entire cart. We confirm all of these vulnerabilities in the real world in 4 levels. We first installed Commerce and Interspace on our own web server. We used our own seller accounts and buyer accounts we successfully did all the attacks. Interspace has a famous hosting service, which is called BigCommerce. We created our own store on BigCommerce and successfully confirmed these attacks. And we really want to tell an end-to-end story, which is the malicious shopper can really go to the real world to shop for free by exploiting this kind of logical bugs. So we found the real stores powered by Commerce and Interspace, these kind of stores, and we checked out physical goods and downloadable goods for free, with less payoff for free. And besides Commerce and Interspace, we are also curious about those web stores whose source codes are not available to us. Can we still find similar bugs? Because we cannot thoroughly check their logics. So we studied the popular store, Buy.com and JR.com. We were able to show that without source code access, some exploit ideas are still applicable. We did
What did you need to modify in terms of software to pose as the attacker? So you are running the web browser, right, where all these transactions are going through. Mm-hmm. What part of that software or the stream that was being communicated did you have to modify? In other words, did you have to modify IE to launch this attack, or Mozilla to launch this attack, or no?
Actually, you have some tools to use. Like in Firefox, you have some kind of traffic monitoring tools. You can monitor the traffic. And also, you may use some kind of HTTP proxy or something, which you can hijack the traffic. You can modify the traffic. Yeah, you don't have to modify the browser.
Okay.
You have a
so
lot
this
of.
was all done without modifying the
We
browser.
didn't modify any
I
browsers.
think the specific tools you use, at least two tools. One is Firefox plugin, which allows you to arbitrarily modify the HTTP request and responses. And in some other cases, actually use Fiddler process.
Fiddler process.
Yeah.
I take it with the closed source sites, not only did you not have the source, you didn't even have the object file, the exe.
Oh.
You had neither source, nor object, nor exe.
Yeah. You want to answer?
No, you said no source code and no what? No.
OBJ and no exe.
No,
And you didn't have any binaries that you could actually reverse engineer or.
So the only thing you have is the two edges of
the communications. We did all the experiments responsibly. First, they were under the close guidance of Indiana University lawyer. Ensure that we were not doing some crime, and we got the support from the dean of our school. And we ensured the following principles: no intrusion to the websites, no monetary loss to the web stores. When we got the product, we either returned the product or we paid the old money. And we communicated all the details to the affected parties. The outcome is quite pleasant because no party expressed the negative points on our test because we're really helping them. They have the bug, and we tell them, you have this bug, you should fix. Right? So, and most of them actually appreciated our responsible efforts.
Was it possible for you to configure these in any ways that you could actually fix the issue yourself, or was it always required that the software providers had to provide a fix?
It is either the web store have to do a fix, or and in some case maybe the service provider needs to do a fix, because the attack is like an attack path. As long as you find a point that you can block this path, then you actually fix the problem. So it's either the web store can fix their logic, or the service provider do something.
You mean CAS?
Yeah, the CAS, yeah, Cashier-as-a-Service, yeah. Amazon published a security advisory in which they credited me, and Interspace even asked if I'm interested in doing security auditor work. After knowing that, I found 4 vulnerabilities in their checkout mechanisms. And our research has been covered by a lot of news articles, which are all positive about how we conducted this research. We communicated all the details with the affected parties. I think this one with the Buy.com customer service is pretty interesting. After we check out a product for free, we send this message telling them that one order was not paid. So Buy.com responded with a generic message telling us just all the possible reasons for delayed charge of credit cards, all the possible reasons. So it's misunderstanding because the payment method was PayPal. Then we send the second message, telling them that I'm a PhD student doing security research, and reused the token. We released this kind of details, and their reply is, based on our record, it will be built on the purchase stage. So we had this difficulty to convince Buy.com we owe them money.
What happens when the material is sitting on the other side?
Yeah. So sometimes this type of attacks, we believe, is not easy to notice by the accounting systems of the web stores. And we finally returned the product after 45 days. That's a refund eligible period, because after that day, they will not refund us. We just return it. They will not start a refund process. Then we disclosed all the technical details, and they finally fixed the bug.
Based on the standard industry rate, how much salary did it cost them to do this paperwork for you? I think they would much rather you stole the item and disappeared.
This is the status of bug fixes. In this process, most parties were very responsive, and the good news is all the bugs has been fixed recently. But like if you are a shopper, may not be a good news because you can never go to this website to shop for free. Yeah. And a particularly interesting one is the Amazon SDK vulnerability. I did not describe it in this talk. It actually affects almost all the web stores which support Amazon payments service. 15 days after our report, Amazon released a new set of SDKs covering all the 5 programming languages they support, and they published a security advisory in which they require all the web stores to upgrade to the new SDKs within 40 days. So this is a pretty serious bug. We also studied the complexity of the case-based checkout logic, which is skipped in this talk. Specifically, we manually extracted a subset of the checkout logic of Interspace, and then we used the Poro, which is developed by Microsoft Research. I think one of the major developers is Cashier sitting here, and we used the Poro to do the verification, and we measured the complexity of the checkout logic. When we talk to some to verification researchers, some of them said that protocol verification tools would have discovered this kind of bugs automatically. So, what is exact contribution of this work? Actually, the real problem is not how to check a formal model such as a protocol against a set of security predicates. This is not the real problem. The problem is there is no protocol. They are just web programs. And the real fun part, like 90% of our research time was on studying this kind of real systems, understanding the operational assumptions of these systems, and the accurate security goals. And without such a clear understanding, we can only say that a given perfect formal model or formal protocol and a given accurate predicate, using the verification technique, you can rediscover these bugs. So the real challenge here is not how to check, but how to extract the logical model and what to check, which is where the system researchers make contributions. A metaphor can be the end-to-end problem here is to find a path in the real world. The verification is a technique to solve the reachability problem between 2 points on a well-defined map. But we need an insightful understanding of the real world in order to draw the useful map, and we are the person to draw the map. In conclusion, we show that multi-party web apps are fundamentally more complicated than traditional two-party web apps. This is from the security sense. Some complexities include confusion in coordination, concurrency, weak bindings, advisory playing multiple roles. We empirically prove that case-based web stores are under imminent threats. And also, due to our research, we also believe that web service integration may become an important area to apply formal reasoning testing approaches. The key challenge is how to extract the model and define security predicates. Currently, we only studied the regular checkout scenario, and there are many other important checkout scenarios, such as subscription, marketplace, gift cards. I believe these are very good research opportunities. Also, the integration of other web services, Facebook, LinkedIn, allowed other websites to access its users' data. Again, you see the similar three-party scenario here. And also, Google, Yahoo, Twitter, a lot of other websites to authenticate users through them. We actually had some encouraging progress along this direction. We really appreciate people from Microsoft and Indiana University for their help on this research. Without them, the research cannot be possible. Thank you. So, any other questions?
Three comments. One is the old USSR had stores where you stood 4 times in line because the cashier handled money and the sales clerk handled goods. And maybe it's worth checking how they did it.
In the real world. Right?
Yes, it's because we have the Western model that the same guy takes the money, gives you the goods. The Russians were way too bureaucratic. The other is, have you read Programming Satan's Computer?
Programming
Satan's Computer by Ross Anderson.
Satan.
Because he expressed one principle that you always name the parties involved. Don't assume, don't let the crypto persuasion come from A or from B or C. Name it and of course secure it. And you take a look at how red tape was used for real with English documents.
What's that?
Yeah, red tape has become a very bad word. What you used to do was you punched holes in documents. You ran red tape through it. You put a wax seal around the 2 ends of the tape. So you could remove documents. You could not interpolate new documents in. There was you need something to tie 2 documents together. And you need, now we need a cryptologic equivalent of that.
Yeah. So I think probably a similar situation here is that crypto does provide some primitives of course you can bind 2 documents by concatenating them and apply a signature, but the art here is how do you apply these messages here? Which one should be the binding should happen between which ones?
Yeah.
Those are not as clear. So the short answer is primitives are there, but how to use them.
Good question. So let me get this on the head. If you were working at Amazon and you wanted to determine how secure your payment system is or if it contained any similar weaknesses, how would you go about doing so?
If I work in Amazon, I think maybe we can go back a little bit. Like we say here, the web service integration may become an important area, and the CAS-based integration is one of these kind of service integration. So I think I should be really interested in this kind of formal reasoning or testing approaches, which to see that if this kind of techniques, how we incorporate these techniques to really ensure that there is no problem. But this is just one technique, because like if Amazon provides this kind of payment service, actually it's hard to ensure that the web store side logic is correct. And so I think he should also spend much effort to help those web stores to correctly integrate the service. And one effort may be provide security conscious guidance, and also provide some kind of automatic tool which can help check their logic if the logic is correct. Yeah.
You're saying it's not just a technical.
It's not just Amazon's problem.
Yeah, it's not a technical problem. It's also cross organization problem.
Exactly.
Yeah, it's a cross organization.
Because it's about the interaction of code from different organizations.
Right.
Yeah.
And I also think the other thing that's kind of coming out, which is a lot of assumptions are being made that are really never called out or never really fully understood, right? And one of
So that brings me to sort of the follow-up question, like, what is the technique here to solve these problems, or are you merely exposing that these problems exist, and what's the solution to this problem? Right?
The solution, once you have found this kind of bugs, then the solution is very simple. You just fix them. I mean, if you know this bug exists, right?
Yeah. Order ID problem, right? So you said, okay, I spliced this new order ID into my URL stream, but that is still, isn't that a legitimate request? Like, I mean, how do you distinguish that from a malicious? How do you distinguish between two URLs? One of which is malicious, of course, you copy pasted it, and another one would be exactly, you intended that to be there, the order ID to be the signature and all. I mean, so what I'm trying to get at is, how do you differentiate these two URLs to be one is malicious and one is right?
So
from the payment.
Binding. The problem there was there's no binding between the order and the payment of the order. So if you created a binding, it's like a time of check, time of use type of thing. So I think the key here is good threat modeling and looking at kind of what you pointed out, what your goals are, and what are the assumptions you're making, and looking at how those interact. But it certainly does get complicated when you're talking about third parties, and you really have to take a look at the whole picture.
Right, so the seller and the cashier service, they have to get better integrated. They have to understand each other much better. And because ultimately your user, the shopper, it will be given some code or some kind of JavaScript, all right, or it is going to open a web page provided by the seller, and any logic that does all these, establishing HTTPS channels, getting URLs, redirecting URLs and whatnot. So your shopper isn't writing any of that code. What you said is that you modified that stream, right? If you modified it in some malicious way, yes, you used a proxy or something in it, but you haven't really gone the next step. Whereas if you were really very malicious bad guy, you would change all of the code that is running on your machine, the user, right? What if you could actually write the damn browser from the start to end, and then talk to your the seller and get the response and change it in any way, shape or form, and then redirect it to the server? So there could be many more malicious things you could have done.
Yeah. And right? I think in current research, what's really done is we don't even have to change the browser side logic or something. We only need to manipulate those data back and forth. I mean, the communication with the web store, the communication with the cache, and we don't even need to change this kind of maybe a set of logic load to the web browser. We didn't even do that, and we still have such power. And if we consider that part, maybe more possibilities.
Like there were bugs. You expose the bugs, and the bugs will be fixed by better integration. But then there is this whole second class of threats, which if you don't assume this kind of, I don't want to use the word benign, but
I think it's assume a completely malicious browser.
Right.
Yeah.
So if you have much more malicious components there, then do you think the solutions, the solution that you're proposing, where the seller and the cashier service have to get better integrated, blah blah blah, will those solutions be able to thwart this problem if your attacker becomes much more malicious and he can change many more things?
So he's asking, the bug fixes that were made for these flaws, would they be valid bug fixes? Even if the attacker model was way more adversarial?
I think that the fix is just that we tell them this bug, and then they find a way to block the attack path. So they think they fix the problem. So I think that they didn't have the.
There's no guarantee. Because you're blocking certain
Yeah,
attack
you just
paths,
block
right?
the attack
I
path.
think the answer should be, in fact, even at this moment, we are assuming the most malicious adversary model, which is there is no logic on the shopper side. Whatever I receive, I can completely mess up with anything. We can just swap the message fields. So I don't know whether there is anything which is more malicious than that, because we have no logic basically. We can do everything on the client side.
Yeah, so what you're saying is you are allowing for that kind of threat model. So you are assuming a perfectly capable adversary that can change each and everything at its end, and it will still work.
Yes, but sometimes this kind of tempering need a fiddler proxy.
Right.
Sometimes it need a Firefox plugin. That's the technical level of detail.
And just to follow up more of a comment, just to understand, sort of make it clear, there's no reason why these problems cannot be solved in practice, right? This is not an impossible problem to solve in practice, writing a piece of code that performs these transactions online securely.
Yes.
Right? So it's just one way to look at this is just that it's a poor implementation of the software that needs to conduct these transactions. Right?
Well, maybe poor design and poor implementation.
Thank you. Yes, absolutely. Right.
Well, but that's like what you have just said can be applied to all pieces of software, right?
Yeah, I agree.
All bugs are like that, right?
Yeah.
And then it's
well, no, actually, let me disagree. Okay. There are problems for which you cannot solve them.
I see.
So I can give you an example of a problem over the internet at large that you want strong consistency with high
performance.
You cannot solve this problem. So, but this problem to me seems like one we could solve. There is nothing. This is not an impossible problem to solve problem. It's just a case of bad design.
It's not impossible, but the thing is, when you consider the complexity that you need to deal with and the scope, how many web stores are out there, so that may be some practical.
Individually, you might be able to solve and create one specific scenario that might be nearly 100% perfectly secure, but it's very hard to say that it's absolutely secure. And then when you take all stores together, all shopping systems, it's nearly impossible to secure them all.
So, any other questions?
Okay,
Thank you.